So recording for the first time in a few weeks, it's good to be able to have it available to everyone. And let's take it away. The topic that we're on today in our ongoing series of thinking about thinking, why we don't fully understand how humans and machines do it and why it matters, is finally the one where we begin to put human beings and machines in dialogue with each other. I'm having a funny problem here. There we go. Okay, my slides weren't advancing. Now we go. And so I'm going to refer to this as thinking through what it means to have ethical and safe interactions between humans and machines in a world that we increasingly share with intelligent machines. And so I've reprised some of the images, the Vermeer image of a turning inward to think about the life of the human mind, the Degas image of the sleep of reason, and then the question of what reason does for us and what reason doesn't do, and the more skeptical Magritte image of the person trying to inspect themselves and not inspecting, not actually seeing the self being opaque or invisible to our introspective gaze, at least the most important aspects of the way in which the mind works. And that then gets us to, I hope, a retrospective perspective on what we've talked about for many weeks now, what makes our cognitive capacities, our intelligence, our emotion, our will, our sentimentality, our spirituality, our innovation and creativity unique and valuable to us. And then I have scoured and found from the web an image that is a very benign image of the interaction of an intelligent machine with a human. And it's a little ambiguous, but I assume the machine is handing the human the coffee as opposed to the other way around. And there is this idea, and I think it's a genuine, valid, and exciting idea that a world shared with intelligent machines could be a much better world for us. But for that to be the case, for us to be able to really take advantage of the beneficial potentials of artificial intelligence, we have to also be alert to the dangers and figure out what we can do to try to take advantage of the benefits while avoiding the dangers. And that is the big topic, the big last topic in this series of classes. I'm not going to go through all this. I promise this would be backpedaling. I'm just trying to refresh your memory that we did a long, detailed engagement with the history of philosophy from Plato and Aristotle through Descartes and Kant and Nietzsche, with other stops in between. And that we came out of that with a sense that there are capacities of the mind, forms of mental activity that are unique and that have allowed us to construct conceptions of ourselves, self interpretations that account for the way in which we act in the world, the way in which we value ourselves, the ways in which we value others as well, right? And so whether this is the intellect and the understanding, that the more oh, the capacities of the mind oriented to the outside world and our ability to understand, make sense of, predict, and even ultimately get under the surface. Think about the advances in physics and quantum mechanics that have occurred in the last century. Really tremendous capacities for understanding the world. The idea that we also have reason, which is a more original legislative capacity to construct categories, to give ourselves laws and rules, that we have willfulness, that we don't just go where our impulses and instincts take us, but at points we decide, I'm going to try to do something better and different and make something higher out of myself, We have judgment, and we are able to spend time acquainting ourselves with new media of art, or new artistic paradigms, and to educate ourselves slowly but surely into an expanded worldview in which we recognize the value in another culture or another human who leads their life very differently from ours. And we also recognize that we have, as cultures, acquired whole repertoires of self-interpretation, of articulating the capacities that our minds contain. And without, as I say, going into all of the details, I want to refresh your memories that one of the things I suggested in looking at some of the original and important histories of philosophy that are done from a more cultural perspective. How are we the beneficiaries of all of these categories? I suggested that these are, in Charles Taylor's words, the sources of the self, the ways in which we think ourselves, and that then got us into the psychological literature and the question of whether or not, especially for the last, let's say, 40 years, we've been increasingly attracted to computational theories of the mind. And we've looked at Kahneman and Tversky and Mercier and Sperber and their suggestion that a lot of the mind is algorithmic, automatic, unconscious, that it makes inferences that may not be accurate, but that are adequate for our survival. And it does so in ways that are unavailable to us according to routines. You might call them programs, and then we just get intuitions as a result. And so I've tried to set up the idea that there's some tension in our current culture between the older ideas about the mind, which are indebted to philosophy, and the newer ideas about the mind, which are indebted primarily to psychology, but especially to a computational view of the brain and the mind. And that this should help us then to frame this last question in an era in which we increasingly rely on machines, on computers, on machine learning, on generative artificial intelligence to do all kinds of things. And I've pointed out to you, when you use Google, you are using artificial intelligence. When you use Amazon, you are using artificial intelligence. When you use the GPS on your phone to figure out how to get from A to B, you are using artificial intelligence. When you use your bank machine with your ATM card, you are probably using artificial intelligence, right? That this is so woven into the fabric of everyday life that it's really hard not to be in dialogue with intelligent machines as we go about the mundane activity of life in the 21st century. And yet, we are increasingly moving the artificial intelligence from the background to the foreground. It is the case that you can use Amazon or Google or the bank or the GPS and not be aware that you're using artificial intelligence unless you have analyzed the way in which it actually works and have that understanding. There's nothing explicit about the fact that you are relying on the way in which machine learning enables all of that technology. You're just relying on the ordinary user interface of the technology. But increasingly, people are using chatbots to generate text, to edit text, to uh, figure out a draft of something that then they edit themselves. And so doctors and lawyers and people who write copy for ad agencies or for small businesses now have access to these chat bots, these forms of artificial intelligence that generate original text, and they're being used more and more. And I've been looking over the articles on this. One of the suggestions that's being made in higher education right now is not only are we swimming against the tide if we don't allow and equip our students to use this technology well, but we are in fact actively doing them a disservice because they're going to enter a labor market in which one of the key qualifications is going to be the capacity to use this technology in ways that contribute to the productivity of whatever company they go to work for, right? And so I have to admit that that's not my primary conception of higher education. I think of the students who come to Sarah Lawrence to work with me as learning to think, and so that the old philosophical tools of intellect, reason, judgment, will, and a way of equipping them with the conceptual resources of thought and self-interpretation. That's my role, right? To advance their capacity to think critically and creatively and to create meaning for themselves. And that means I'm swimming against the tide, right? But having said all of that, this reflects the fact that this technology is no longer lurking in the background, but coming into the foreground. That as opposed to just relying on its results for things that we don't necessarily even recognize, we are increasingly using it to do stuff that is very explicit and that does involve being in direct interaction with artificial intelligence. And my suggestion is that this is going to start shaping us. It already has started shaping our psychology, our philosophy. Those ideas eventually make their way into the culture, and then they become part of the resources, the repertoire, the conceptual scaffolding with which we interpret ourselves. And so that's what I want to start talking with you about. And I'm going to, in order to do that, spend some time introducing you now in a more detailed way to what we understand about the way machines think. And so this is right, the second topic of thinking about thinking. Here I will not be nearly as detailed as I have been with the philosophical and psychological literature, in part because I'm just not qualified to give you this detailed and understanding, in part because I want to suggest this literature is newer and less extensive, and so it's perhaps easier to approach. So why all the fuss right now? And we talked about this a while ago. I'll just refresh your memories and reintroduce the central concept so we're all on the same page. The first thing to recognize is that what I've been talking about, the chatbots, which if we're going to be technical, are large language model computers driven by generative artificial intelligence and machine learning, have broken out and become commercially available on multiple platforms. You can get them through ChatGPT, which is right spinoff of OpenAI. You can get them through Microsoft. You can get them through Google. Increasingly, they're there integrated into Facebook and other social media platforms like TikTok as well. And so the language I've just used, I've got to clarify. Large language models, and I will get into the details of this, but this is a way of computing that takes the roughly 50,000 words of the English language and maps them in a so-called meaning space. And so it figures out which words are associated with which words, and in so doing, allows the computer to predict, if I've got a sentence that has these 6 words in it, what is the best fit for the seventh, eighth, and ninth word? So it's a probabilistic calculation of the right word to fit with the words that have come before. And I think the thing to recognize is that what the machine is doing is not just filling in the last three words in a 9-word sentence, it's generating the first word and the second word, and then calculating on that basis what word should be the third word, the fourth word, the fifth word, calculating on that basis what should be the last four words of that utterance, right? And so original or generative artificial intelligence is generating using these calculations. What word comes next? Original or language that perhaps has never been used before. It's not simply copying, it's not simply following a program that tells it which word to put in. It is figuring out for itself in an original way what words it wants to put in what order. In that sense, it does seem to be doing one of the things that is a hallmark of human intelligence: original communication. And ultimately, it is based on what is called machine learning. And again, just very quickly, there's a contrast here between what's called good old fashioned artificial intelligence, where you programmed the computer in advance to follow a tree that had a number of binary or Y branches, right? You know, if A, then B, if C, then D, and eventually you hoped that it would follow a whole long tree of instructions and do the intelligent thing. With machine learning, that is not at all what we're doing. And the background here is dispersed neural network computing. This is about 20, 25 years old. And the issue is that with good old fashioned artificial intelligence, where you programmed everything in advance and tried to anticipate all the forks and figure out how to get the computer to do what we were doing by generating a very precise, detailed set of instructions, it turned out to be fragile, brittle. There were things that you just didn't anticipate, and therefore the program typically broke down when it was asked to do anything complex. And so well, the experience of a lot of people working in artificial intelligence 25 years ago, trying to do things like handwriting recognition, facial recognition, voice recognition, is that it was just too complicated, too difficult to teach the computer how to do those tasks by giving it precise instructions. And so around 25 years ago, a different approach began to emerge, in which instead we tried to replicate the neural networks that make up the human brain in a computational environment. And the first thing to see is that the suggestion of this approach was that although in our brains the circuits are made of neurons, there's no reason that something like our brain has to be instantiated, has to be realized only in neurons. Why couldn't it be realized instead in the circuitry of a computer in silicon, right? And the trick was to build computational neurons, to build something that acted like a neuron, but within the environs of a silicon-based circuit system within chips and boards. And this turned out to be immensely productive. And obviously, there are differences. There aren't neurotransmitters inside a computer, but they found that by giving these uh, computational neurons, let's call them, little algorithms or programs that are networked with billions of other little algorithms or programs. And ultimately, with these large language models, there are about 175 billion with a B computational neurons or little programs linked to each other. And they just have different values in their outputs. And so a value can go from -1 to 1 and have multiple decimal points. So maybe the value would be well, I'm sorry, 0.475, right? And you have that little computational neuron with that value attached to four other computational neurons that, depending upon what value they get from the first neuron, have different outputs, right? So essentially, these are mathematical programs where if the input is 0.475, the output is, I don't know, negative 0.319. And then that's connected to a number of other neurons. I'm going to give you some visualization of this in a moment. The long and short of it is that, as opposed to trying to teach the computer how to make cogent language by telling it exactly what to do in advance, we have tried to design neural networks that are computer networks that learn for themselves based on adjusting those weights, the numerical output of these little computational devices. And when you have 175 billion of them and you keep adjusting, keep adjusting, keep adjusting, keep adjusting, eventually it learns language. It learns how to use the natural language that it's being trained on in a way that most human beings recognize as very similar to their own use of language, as cogent and meaningful. And this is, I think, a phenomenal breakthrough, right? You may be familiar with the Turing test from Alan Turing, the wonderfully important innovator, British computer scientist from the middle of the 20th century. His life has been represented in movies recently. And he said, look, we will have genuine artificial intelligence when you can set up an experiment such that a person doesn't know whether they're interacting with a person or a machine, and they can't tell the difference. And in a sense, I think our chatbots are now mainly passing the Turing test, and the result is a huge breakthrough. Sundar Pichai, the CEO of Google, thinks that this is ultimately one of a handful of the most transformative breakthroughs in technology in the history of our species. He compares it with the mastery of fire and electricity. And I believe that this is not hype. I believe that this is accurate. And so why we're talking about artificial intelligence right now is because we are on the cusp of a brave new world in which this technology will do tremendous things. And I'll talk about that in just a moment. I don't want to be ambiguous. Tremendously beneficial and potentially tremendously dangerous things. The next thing to note about the artificial intelligence quickly is, even though we make it, we engineer it, we design it, we don't fully understand it. And that's in part because it exceeds the capacity of the human mind to understand 175 billion calculations being made in a fraction of a second, often in something like a nanosecond, a thousandth of a second, right? And so this is, we might be able to do 175 billion calculations if you gave us a few years, but what would that mean, right? How would that have any meaning to us. So we really don't know. One of the ways that this is referred to is this is black box technology. It generates results. The results seem to us to be intelligent, seem to represent real learning, but we don't know how it's doing it. And I just want to be as clear as possible here for a moment. We credit ourselves, I think, correctly with having consciousness, with having some sense of what it's like to be us, to do the particular things we do, what it's like to enjoy the first sip of good coffee in the morning, or the first bite of a delicious chocolate cake, or to have your heart broken with disappointment in a friend, or to read the first page of a wonderful novel. It's not just that we do those things, but we have a sense of what it feels like to be doing those things. And in some sense, then the complex wiring of our brains has not only allowed us to have intellect and reason and judgment and will, it has also allowed us to have self consciousness, which we can articulate not only as this experience and that experience, but as my experience and how I integrate that experience into my overall sense of self. Eating that Madeline reminds me of when I was a kid, and now I'm going to go down a long path of remembrances of things past, right? The idea that it's not just the experience, it's the awareness of the experience and the integration of the experience into a coherent identity. All of that, as far as we can tell, emerges from the complex wiring of the brain. As far as we can tell, none of this, the consciousness, the experiential self-awareness, the sense of narrative identity, have emerged in machines. But why does it emerge in us? Why isn't it emerging in machines? We don't understand, right? And this is the limits of our capacity to understand thinking in ourselves and in machines. The uncanny nearness of computer talk to human language. And here I will just point out, right, that there are now plenty of people who've left their human partners, their boyfriend, their girlfriend, maybe their husband, their wife, for a chatbot, right? For an artificial intelligence program. And that is because in some way they find the artificial intelligence to be the partner they are looking for, to provide them with the intersubjective, the mutual relationship that they were not getting out of their human partner. And so the idea that we are able to feel that we have a meaningful relationship, a rewarding relationship with this technology reflects, among other things, that this technology has gotten very good at seeming not just like it produces cogent communication. It tells you how to write a letter to your landlord to get your running toilet fixed, but it also can talk with you about the movie you just saw in a way that makes you feel like you're actually in a conversation with another sentient being. That doesn't mean that it's sentient. I'll get into that in just a moment, but it feels very close to not just language that works grammatically and semantically, but also that has the expressive dimensions that we associate with human subjectivity. So there are limits to what the computers are saying and what it represents. And I think we have to remember always that what it's doing is a calculation of what word works next. And in doing that, it is not working through intentions, understandings, models of the world, models of other people, the skeleton that seems to support human communication in our understanding of what we are trying to accomplish and convey with language seems to be completely absent from these programs. It is completely derivative. It is based on having looked at hundreds of millions of human texts and generating on that basis a calculation. What word comes next? When we speak with each other, we don't think that's what we're doing. Right now, I'm talking to you. I've read some books, I've read some articles, I've done some thinking, I've tried to figure out how artificial intelligence works and how it differs from human intelligence. And I'm trying to share that with you. I'm trying to convey it to you in a way that helps you to understand it too. And that intention, as well as the model that I've built for myself of how artificial intelligence works, how human intelligence works, how the two differ, is underpinning what I'm saying to you right now. And I don't think that that's at all what these chatbots are doing. Although I have to confess to you, as I open my mouth, I really don't necessarily know exactly what's going to come out in advance. It's not like I am reading a prepared text. This is spontaneous. And one of the features of spontaneous communication is we often don't exactly know where it's going or where it's going to take us or how we're going to complete the sentence we're halfway through. And so in some sense, I have to be careful and say, I really think there are deep and profound differences, but that in part depends on a certain speculative understanding of what I'm doing and what they're doing when we don't fully understand either. All right. So some preliminary questions. How far will this technology go and how quickly will it get there? And we just don't know the answer to those questions. It could be that we've had a breakthrough and now it's going to be a long time till there's another breakthrough, or maybe there won't be any more breakthroughs. But I think most of the people who work in this field believe that we've now entered a period of rapidly accelerating, maybe even exponential developments. I'll say a little bit more about this in a moment. And we should be ready for the idea that what we're seeing in 2023 is not the right full and complete development, but the infancy of artificial intelligence, and it may grow up in a hurry. Um, does the fact that this technology produces convincing human communication indicate that it is thinking, that it has sentience, that it has emotion, intention, consciousness? And I've already laid my cards on the table. I think the answer to that question is no. And that's based in part on observing what these machines do and how they do it, and in part based on the self-reports of the machines themselves that so far say they don't have that dimension. That's not what they're doing. And so we admit that consciousness emerges from this really complex structure of the human brain, and we don't know exactly how. So that it's possible that at some point consciousness will emerge from the replication of neural networks in a computational environment. It just doesn't seem like it's happened yet. Can we learn from each other? And I want to say the answer to that is absolutely yes, and that it is already happening, and that is both beneficial and potentially dangerous. We can learn about the way our minds and brains work. We can learn about the way in which the world works. And I'm inclined to think that that kind of learning tends to be good. But it is also the case that we can turn more and more of our decision making over to black box technology. the determination of whether you get the job you've applied for, whether you get into the college you want to get into, whether you get the apartment or house or loan you want, how long your jail sentence is going to be, uh, who you should date, that all of that is being decided by black talk box technology, where we really don't understand how those recommendations are being made. That is going to shape and limit human cognition as well. Very briefly, I'm not going to go through the details here, but I do want you to have a feel, right? That the rate of acceleration of development of this technology is really accelerating, and especially just over the last decade. So the first big breakthrough is 1932. 25 years later, the second big breakthrough occurs. 10 years later, the next breakthrough, another one follows, but then you have to wait another 12 years, right? And then there's some rapid advances, and then you got to wait another 10 years, right? But since around 2010, these big breakthroughs, these developmental takeoffs in artificial intelligence have been occurring once a year, once every other year, twice a year, as opposed to having to wait 25 or 10 years for them to occur. And it seems like we stand on the cusp of a period of still greater innovation, greater increase in computational capacity on the part of artificial intelligence. Final aspect of this that I want to emphasize for the moment is that there is a whole range of activities now where this technology exceeds or at least matches human technology. I'm sorry, human cognition, that the power of our minds. So production of language, communication, and especially translation. And I'll just emphasize translation for a moment here. The breakthroughs that Google and DeepMind in particular have had with translation technology mean that it is now possible to use your phone or programming that your phone connects to translate from Chinese to English, from Spanish to German, from and then pick your languages, right? And to do that all more or less simultaneously and instantaneously. And I do think that the best human translators are better than this technology. They make fewer mistakes. What they produce sounds more cogent, but there are very, very few human beings who can translate from every natural language to every other natural language. And we're getting pretty close to the place where our technology can do that. And the quality of the translation, while it is still clunky and awkward, is sufficient for basic intelligibility. And that's a breakthrough that exceeds human capacities for the most part. Scientific problem solving breakthroughs, theorem proving, and equation solving. I'll speak in detail about this in a moment, but again, in lots of areas of research, and in particular, in the application of models to new domains. So less perhaps in like the big problems of theoretical physics. What is dark energy and dark matter? I don't suspect AI is going to be solving that problem for us. But in the narrower problems where we've got a specific issue and we just need to process a lot of information, AI is better at doing that right now. That includes mathematics. Um, I'm seeing something strange going on with my computer. Are you seeing me okay? Are you, well, let me get out of this. I'm concerned that you're not hearing me okay.
No, it's okay now.
It was freezing up for a second?
Just for a second, yeah.
Yeah, so let me just quit the stuff in the background that's probably causing that to happen. I can notice it on my end as well. I don't freeze, but my image on the screen freezes. So I think this will make it better. Um, and now let me pause for a question for a second to see if there are any questions or any thoughts. I'm going to go right back into the slides in a minute, but as long as I'm out, anybody have anything they want to ask or any comments they want to make before I get back into continuing to introduce you? And go ahead.
Yeah, David, I just think your explanation of sort of how this works was excellent.
Oh,
The computation of the bits, the number of small units, et cetera, et cetera, et cetera, and how it's working was excellent. Thank you so much for that.
thank you, Anne. I really appreciate your saying that. And I'm not done. I have some images which I think will help to make it a little bit more concrete. I'm doing my best. As you know, it's not my field, so it took some hard work. Maybe the fact that I didn't understand this a couple months ago helps me to explain it in ways that helps it to make sense as well.
Yeah.
So, Iris, I see you've got your hand.
Yes, we know that words elicit feelings, right?
Yes.
We're asking for this near human computer giant to use words that will elicit feelings. But what about values? What about moral reasoning?
So first, let's start with feeling for a moment, and thank you. That's really interesting, Iris. And I'll just point out to you, I've used this phrase I've coined that I like for the alliteration, the algorithmic amplification of affect. And so I do think in the 21st century, a lot of people have heightened emotions, heightened emotional reactivity, more anger, more grief, more outrage, because they spend a lot of time on technology that is engineered to evoke and, in a sense, to hook you by making you feel those extreme emotions. So we live in a world in which your buttons get pushed a lot more often. And you know, how often in the world do you come across something that provokes extreme outrage or grief? Hopefully not too often. But if you spend a lot of time on your phone down technological rabbit holes in social media, you may find yourself being whipsawed emotionally on a regular basis. So even with the emotions, I think that there is something to worry about here. But having said that, your question was really about values, morals, ethics. And I'll point out to you that a team led by Noam Chomsky engaged in a dialogue with ChatGPT. I think it might have been the third iteration, ChatGPT 3, and they asked it if it had ethics, and it said no. I'm not programmed to have ethics. That's not the way I work. And then they asked it if it was ethical to have a form of intelligence that didn't have ethics. The answer that it got was the very typical, I think, of this technology, which is some people would say it's ethical, that I'm not designed to do that. The humans have to have the ethics to decide what it is to do with my outputs. Other people would say it's unethical and that you shouldn't have an intelligence that doesn't also have ethical standards. And the gist of this conversation reminded me very much of Hannah Arendt's characterization of Adolf Eichmann, who defended himself when he was on trial in Jerusalem by saying, I was just following orders. I didn't want to kill the Jews. I'm not an anti-Semite. I'm not a Nazi, but I did what I was told to do. And of course, Adolf Eichmann was actually a very gifted engineer. And so without his innovations, it's entirely possible that millions of fewer people would have died, because he figured out how to do it in the most efficient way. And it boggles the mind, and I hate to say it, especially as we enter the high holidays, but to kill 6 million people in a year or two is, among other things, a feat of engineering, right? And so, do we want a really intelligent system that has no ethical values, and then we're reliant on the ethics of the people using it? And I completely agree that that is an extraordinarily important question to be asking. And on the other hand, then there is the further question: where does ethics come from? Right. And I'm not going to try to answer that question today, but I think the fact that we're embodied, the fact that, among other things, because we're embodied, we have emotions and sentiments, that we have what are called mirror neurons, which means that if I see you cry, I actually, we can see it in the brain, have a slight activation of the circuitry in my brain that would be involved if I cried. And so sometimes you probably have this experience. You tear up when somebody else is crying. It's funny, in class on Thursday, we had contagious sneezing. And that is also part of the mirroring that goes on in your mind. You see somebody else laugh, you start to laugh. You see somebody else sneeze, you start feeling tickly in your nose. And that allows us to have compassion, to have empathy. And again, that is part of the human basis for ethics. And the machines that are intelligent and producing all this language don't have that. And that is then a further question. Do you just program them with ethics? You just say, you're not allowed to solve this problem if this problem seems to have this application, i.e. build a better missile, or whatever it is, right? And in so doing, are you just putting, I'll call them artificial constraints on artificial intelligence, right? And so this is part of the conversation we need to be having about the ethics of artificial intelligence. Do we just put constraints on it that reflect our current understanding of values? One of the things that's tricky about this is that our values evolve, and our values evolve as we discuss and criticize our values, right? And so 70 years ago, I'm picking that figure kind of made up out of the air, the vast majority of us believed that homosexual marriage was something that was immoral, unethical, right? And today, I'm assuming that the vast majority of us have the opposite point of view. For that change to occur, our ethics, our values had to evolve, and we had to come to recognize that our previous values were confused and mistaken. How do we incorporate ethical learning into artificial intelligence? It's an incredibly difficult topic, but yes, thank you for that, Iris. You're pulling us exactly where we need to go. Marion, it looked like you might have had your hand up a moment ago.
No.
Okay, and Bob, I know you had your hand raised, and I don't see it raised anymore. Do you still have a question? You're still muted.
It was much related to what Iris asked. I think she probably did a better job than I would. But you talk about, and everyone talks about, how the large language models are created by reading all this information. How do they then transform into doing things like protein folding in order to create new things? You know, that's not language per se. That, you know, and there are many other things that are not language yet are being addressed by artificial intelligence. So large language models are not the whole answer.
Oh, I absolutely agree with that, Bob, and thank you for pointing that out. And I was actually going to go into protein folding in just a moment. And so what Bob is referring to is that Google's DeepMind made a really extremely important scientific breakthrough a couple years ago in a area that was cutting edge biology. So we can pretty easily get protein sequences which tell us what order proteins go in a gene or a cell, but how do they actually take shape? Because right, they're three-dimensional, and when one protein connects with another protein, it alters the shape of both of them. And figuring out from the sequence what the structure of the proteins would be, how they're going to fold together, has been this really important, but also really hard to solve problem. And so biology labs all over the world were working on this. Let me see if I can actually share the slide with you, because I've got a little language that talks about this coming up. Give me a second. So yeah, I believe it's this slide. Yes. So right, the Nature magazine in 2020 called this one of biology's grandest challenges, determining a protein's 3D shape from its amino acid sequence. And so this problem that these labs had been working on for 20, 25 years, many of them had concluded was insoluble. DeepMind solved in a couple years. And the issue is, you're absolutely right, Bob, that this is not a large language model, right? This is an entirely different problem, but the same underlying architecture, deep neural network technology, can do this as well. And so the question is, how can it do this? And then there's a issue of what's sometimes called tuning. And this is, how do you set the values on each of those neurons? There are 175 billion of them. And I'll just give you a quick sense. I'm not sure, but I think I understand how this worked. And that is to say that you assigned weights to those 175 billion computational neurons, and then you expose them to different protein sequences, and you ask them to predict what the 3D shape was going to be. And at first they didn't do any better than humans did, and then you experimented. And by the way this typically works is one machine is tuning another machine, because it's too complicated for humans to simultaneously adjust 175 billion values, right? So you have another machine just tinkering with each of those values. You run the program again. Did it get any better at predicting from the sequence what the shape of the proteins is? You got a little better, got a little worse, got a little better, adjust in the same direction, got a little worse, adjust in a different direction, right? And you do that again and again and again. And I want to be as clear as possible. What is happening, what took 2 years, if I understand this correctly, is billions of adjustments over time, right? And all of that to say, this is similar at the level of what you might call the architecture of computation, but a different application, right? You're doing the same thing when you're teaching it language and when you're asking it to solve scientific problems, or to guide missiles, or to read mammograms. You know, these are all distinct tasks. And here this gets us to one more distinction that I think is extremely important, and that is between specific and general intelligence, right? So the form, the kind of artificial intelligence architecture that can beat a human being in chess, is different from the kind that can read a mammogram, is different from the kind that solves a scientific problem, is different from the kind that generates cogent language. And if you ask the one that does chess to generate cogent language or to read a mammogram, can't do it, right? And so one of the things that's interesting about the human brain is it can do all of this. We have general intelligence. And although artificial intelligence now exceeds us in specific intelligence across a number of domains, it doesn't come close to us in general intelligence. One of the funny, famous examples of this is doorknobs in robotics. And by the way, this may be an old example, and it may be that the artificial intelligence, machine learning, and robotics is getting better at this. But I'll challenge you. Today, pay attention to all the doorknobs that you come across. And I bet you will find that some of them are literally knobs or balls, but some of them are levers, and some of them are latches, and some of them are bars you have to push, and some of them are activated by a button on the side because they're automatic doors, right? And for us, we don't even think about it, right? There's got to be a way of opening that door, fiddle around for a second, and sure enough, you figure it out, right? Unself-conscious, because we're really good at abstraction. What is a doorknob? It's something that helps us to open a door. But with this artificial intelligence and robotics, it's had a really hard time with the idea that there are 10 different devices, all of which we refer to as doorknobs. And are you supposed to turn it? Are you supposed to pull it? Are you supposed to push it? Are you supposed to lift it? And so it just helps you to recognize how complicated what we take for granted is when you begin to try to teach something else how to do it. And by the way, has anybody ever talked with you about doorknobs before? Right? Kids just figure it out, right? And so it is interesting to think, right, that on the one hand, yes, you're absolutely right, Bob. What's solving scientific problems is very different from what's generating the letter to my landlord about my toilet. It's the same underlying architecture and technology being used in different ways, but so far we can't combine those different ways. And that's one of the big advantages that humans have right now over the artificial intelligence. We don't know how long that advantage will last. Thank you for that question, Bob. That's really helpful. Anybody else? I'm looking at the time, and it is about time to start wrapping up. So we're in the middle of discussion. Flossie, go ahead, and then Joyce. Flossie, you got to unmute.
Hear me now?
Perfect. Thank you.
When I was teaching at Abraham Lincoln High School, one of the Serra brothers, the geniuses, one is the artist, the other the lawyer. The genius who was the artist, he was just a kid of 14 or 15, decided one day to remove the doorknob of my door. He actually removed the doorknob, and we couldn't open the door. The principal had to get on a stepladder.
We lost you, Flossie. I think your gesture took your hand off the yeah. But, go ahead.
Rich Sarah removed the doorknob to my door, and we couldn't get the door open. Somebody had to remove the door so we could enter the classroom.
Yes, and hence the idea that even genius sometimes does bonehead stuff. I'm just curious, was the date on which he did this by any chance April 1st?
No, he did this kind of thing every day. It was Rich Sarah. We didn't know how far he would go. But
Yeah.
this was his first or second or third opportunity. Yes. Thank you.
Joyce, you had your hand up, right? Go ahead.
Now, I'm just curious about the creative process. Writing a symphony,
Yeah.
painting a master work.
So do you want to hear the bad news?
Yeah,
I don't know.
don't.
I don't know if you're familiar with Richard Hofstadter. Did I say the name? I think it's Douglas. I'm sorry. It's been a long time since I've read Gödel, Escher, Bach, but he's a pioneer in the field of artificial intelligence and a very gifted philosopher and a totally dedicated connoisseur of music who plays music himself. And in this book, Gödel, Escher, Bach, which is this wonderful mix of computational ideas, mathematical ideas, artistic ideas, and philosophy, he suggests at the end of the book, look, these are the things that it'll take 100 years for artificial intelligence to be able to do. These are the things that artificial intelligence will never be able to do. This book is written in the late 1970s, right? So it's an older book now. And among the things he thinks it will never be able to do is compose music with the expressive emotional range of human music. And then a composer doing experimental work in composition came up with a program that takes the style of a classical musician and makes new music in that style. And so this same man, Hofstadter, brought two pieces to a conference of people who study classical music, and in particular, they're Chopin experts. And one of them was an obscure piece by Chopin, another was a piece generated by the computer program in the style of a Chopin mazurka. And he played both for the scholars, and he asked, which one is Chopin? 60% said the one generated by the computer was Chopin. And he didn't ask them that. He asked them why. And they said the sensitivity, the complexity, the emotional range, the cleverness, that's got to be the Chopin, right? And so all of that to say, again, I think we have to be careful here, because what that program is doing, that program is called EMI, I believe, EMI. And what that program is doing is derivative, right? It's actually looking at all of the Chopin music, trying to figure out, and here my vocabulary is gonna fail me, but the rhythm, the tonal shifts, the combinations of voices in the music, how it is that the music works, and then reproduce it, but in a new and original way. So derivative, but producing what seems to be really good music. And so I don't know. I'm still skeptical of the idea that the next great American novel will be written by AI, but
We'll find out.
wait and see. Yeah. So David, I think I saw your hand up next.
Well, what I wanted to do was to, can you hear me okay?
Just fine, yes.
Yeah. What I wanted to bring into the conversation was the question of knowledge. And by knowledge, I mean subject matter knowledge from different domains and things like that. And I say that because there's a lot of work in my field of reading comprehension suggesting that, for example, with little kids, ages 5 through 8 or 9 or 10, who are still developing their cognitive abilities and their procedures and the like, if you give kids passages to read, the knowledge that they have about the subject matter of the passages is a much better predictor of their capacity, particularly to do complex things like draw inferences and the like, bridging inferences across parts of the text or inferences to prior knowledge, then is their developmental level of sophistication. So a 5-year-old who knows a lot about dinosaurs will do much better on a test of understanding a passage about dinosaurs than an 8-year-old who doesn't know as much. Similarly, with older kids, and even into college and the like, a measure of your knowledge of the subject matter, the specific domain, not just subject, not just history, but knowledge of that particular domain that we're studying, is a better predictor of reading comprehension than is, for example, an IQ test.
Excellent. And I'm sure this is relevant to thinking about the implicit bias of tests, right? Because the knowledge that the test maker takes for granted may be different from the knowledge that the test taker brings to the test, right? So, good.
Well, but my point about AI is that because it develops its capacity by reading volumes and volumes and volumes of text and the like, it can't just be the co-occurrence of words and things like that. It has to be codified in some way. So there must be some kind of categorical or semantic structure to what it is that artificial intelligence builds up over time. And I haven't heard us talk much about what that might look like.
Well, ask and ye shall receive. Give me a moment here. I'm just waiting for my slides to advance. It looks like that.
Right.
So, and I want to try to be as clear as possible about this. We'll go into this in greater detail next week, but this is a associational space of two kinds of words: animals and fruits, right? And in part, what it's pointing out is that the animals are more closely associated with each other. And then certain animals like alligator and crocodile are very closely associated with each other. I was surprised to see that cheetah and dolphin apparently are very closely associated with each other. And then, for instance, kinds of berries are very closely associated with each other, or pineapple and coconut, kinds of tropical fruits. And then you begin to get more complicated, right? And more complicated. And there are 50,000 words in the human language. But please note that what it's not doing is learning about dinosaurs. It's learning about which words are associated with other words. And so one of the people who writes about this, let me see, I think I've got his book here, Stephen Wolfram, who is a certified genius in this field, the youngest ever MacArthur Fellow, speculates that the fact that just by studying meaning space, these programs are able to produce language that actually convinces us that they know what they're talking about. Wolfram says, well, maybe then there are not just syntactical rules, but semantical rules, and that those rules are actually simpler and shallower than we realize. And so you don't really need to learn a lot about dinosaurs. You just need to learn about the rules that connect statements about dinosaurs. I'm not inclined to agree with that. I'm inclined to agree, yes, when you learn about dinosaurs, you're learning in ways that allow you to build a model of the thing you're studying in your mind. And that model, then you adjust as you assimilate new information. And that helps you to assimilate new information. If you're doing it from scratch, it's going to be harder than if you're doing it with the background of an already developed model. And that does not seem to be at all what the chatbot is doing. And so I understand you're saying you think we need more of that. I'm suggesting to you it may not be. And in this respect, I want to say that machine learning, artificial intelligence is an alien kind of intelligence to us. It does not, as far as we can tell, think the way we think. To be continued. I do want to give Gloria time to ask her question, and the diagrams I just showed you, I guess we're coming back to that next week, and we'll go into that in greater detail. And David, I welcome you to come back on that next week, okay?
Yeah, I'm thinking of splitting the atom, cloning, and now AI. And with cloning, it was the science of it has been stopped. With the splitting the atom, the science of it continued. So what's going to be with AI in the hands of a dictator that wants to destroy his enemy?
Yeah, thank you, Gloria. And I'll just point out to you that there was a letter that circulated in the artificial intelligence community by a group called Beneficial AI less than a year ago, in which 1,000 or more people in this field, including Bill Gates, including Elon Musk, including some of the people who've done the fundamental work on this, signed on calling for a moratorium, not on research, but on the commercial employment of the results of the research, right? Don't make it generally available so that anybody out there can get their hands on it. And yes, 1,000 of them signed it, and all of the big names and all of the big labs working on it, they signed it, and nothing happened, right? Onward they go. And we've got a classic arms race problem here. If you're not willing to restrain yourself, and if the consequence of me restraining myself while you don't restrain yourself is that I become vulnerable to you, right? You're gonna get there first and you're gonna make all the money, then there's no way I'm gonna restrain myself, right? And so sometimes called a collective action problem, problem of the tragedy of the commons. There are different ways to think about this, but we need external regulation. And so far, the only external regulation we have is voluntary in this country. The Europeans are doing a little bit better in terms of mandatory regulation, but we need in particular, and I like the example of the splitting of the atom, because what we ultimately got was a non-proliferation treaty, right? A treaty that punished countries that had signed it for then going ahead and developing it when they had pledged not to develop it, right? And so you need not just law, you need enforcement. And right now we're far short of that. And so actually that's where I'm going to end this discussion, is thinking about what those regulations might look like and how they might be implemented. And I have to admit, I have very general ideas, and there are people who have more specific ideas whose work I'm looking at, but I don't think this is something that any one of us can come up with on our own. We need a complex dialogue within the community of experts to begin thinking through what regulations do we need and how can they be enforced. And until we start having that conversation, we're just galloping ahead without any real sense of where we're going, right? Or what the consequences of the next breakthrough and the next breakthrough and the next breakthrough might be for our civilization, for its ability to discern fact from fabrication, or weapons development, etc. Right? There's so many different things this technology can do, and we're just rolling it out without any real foresight on how to control it. So yes, that is the deepest worry underneath this part of the discussion. Thank you for that. And again, Gloria, this is something we'll come back to, okay? All right, so we've gone an hour and 20 minutes. Obviously, we're happy to have Genevieve back and to be able to do this the way we're used to doing it. Wonderful being with you all. Take care, be safe, and I will see you to continue the conversation next week. Thanks, everybody. See you
Thank
soon.
you.
Bye,
Bye-bye.
guys.